Okay, so I was gonna play some chain song that Stevie Nicks has, but we'll leave it at notes. All right. So are you familiar with what's called a composite function? This is what chain rule has to do with.
Is it related to composition?
It literally is a composite function. So like if you have like, say you have f of x and you have a function g of x, and let's say f of x, let's go with u cubed, and let's say g of x is x squared plus 4. So two functions, and we're going to do a composite function. And that composite function is going to be known, so basically f of g of x.
Oh, I remember.
So yeah, that's what this has to do with. So as an example, this would become x squared plus 4 cubed. So think of this as the outside function. The u is the outside function. That's your u cubed. And this x plus 4, or the x squared plus 4, that's simply the inside part of this function. So if you think of it that way, that's how the composite function works. So that's just a foundation concept that is the first thing we're going to talk about. So we're composing functions just the same way I can do f of g of x, I can do g of f of x. So remember that as well. In this case, f of g of f of x would be really hard to do. Unless we did u cubed squared plus 4. That would work. If I did, so again, this would be u cubed, excuse me, not u cubed. Yes, u cubed, my apologies, u cubed squared plus 4 is a possibility. So if you just keep in mind that the u cubed part of the function is your f of x part of the function. And so I'm inserting this part into g of x, and g of x is all of this, right? Having said that, I'm going to do example 1. And this is how they explain it. So I actually like this explanation. It said, let f of u equal e of u, e to the u power, and g of x is going to be equal to negative 3x. And so what they're asking us to do in this case, and if you look at the simplicity of this, they're asking you to do f of g of x. So we'll start with that, and then they say, secondly, to also find, after you find the first part, is find g of f of u. Okay, so we have two projects to do here. So if this is f of g of x, this is f of negative 3x. And this is now, instead of e to the u, this will be e raised to the negative 3x, where the u part of the function is this part that we're inputting. Remember, u is right here. Okay? They also asked us to find g of f of u, which in this case, if you look at g of f of u, look at this area here for a moment, you notice this becomes g of e to the u power, which is equivalent to negative e to the u. So we're substituting e to the u in there. In Chinese? Or is it making sense? Making sense?
Makes
All right,
sense.
good. All right, let's try one. And so this relates directly to this, so we're gonna do a try here. We have, so same thing, let f of u equal to u, and g of x equal to e to the x. They want us to find f of g of x, and they also want us to find g of f of u. All right, so I'll give you a couple minutes to take a look. So what are you thinking for this one?
For f of g of x, 2e to the x.
There you go. 2e to the x. So in other words, if you have g of x, which is e to the x, we're substituting it into that part of the equation. Right? Composite, basically. Okay. In the next part, they say if I have g of f of u, what do you think that one's going to be?
2e to the u.
E raised to the
Power
to u. Yep. Okay. You comfortable?
Yeah.
Yeah. All right. All right. Example 2 is very similar. In example 2, we're still running on the composite. So the question is asking you to write each function as a composite of two simpler functions. So they start us with example A, where we have y is equal to 100 natural base e to the 0.04 x. All right, so this time we're going the opposite way. We're splitting it up. We're breaking it up. So I'm thinking I could re-express this as u, which is equal to the function of u, equal to 100 e to the u power. I'm also thinking then that I can express this value u, which is equal to the g of x, and this breaks down into 0.04x. Does that not make sense if I were to substitute it back in? So I'm literally breaking this u as this is being u, basically. And the g of x goes into u.
Okay. You're doing the exact thing.
Exactly the opposite, correct.
Okay.
You put your shoes on in the morning, and when you get home, you take the shoes off. Kind of like the same thought process.
It's like you're putting on the socks and the shoes, and then you take the shoes and the socks off.
Correct. That's what you're doing. So in part B, they give you one more little example. And they say, okay, well, what if we give you y equals the square root of 4 minus x squared? What do you think? What is the f of u in this case? What's the exterior function?
The square root.
Yeah, so y equals f of u, which is equivalent to the square root of u, and our u, which is equal to our g of x function, should be the 4 minus x squared. How do you feel about that? All right, let me give you 2 to try on your own. Oh, sorry. Can't read my own handwriting. I don't know what page is what. That's awesome. All right, so try this one. Same question stem I'm giving you for part C. Let's call it part C. Y equals 50 e raised to the negative 2x. And for part D, I'm going to ask you to take y equals cube root of 1 plus x cubed. Tell me what you think the answer should be.
First one is minus 100 e to the x.
Oh no.
No.
Remember, we're not differentiating. We're splitting it up. This is
Oh,
composite function. So how would you split this composite function up?
50e to the, yeah.
Yeah, 50e to the u power. And the second, so this would be considered f of u, 50e to the u, and then g of x part of the function would be where u is equal to negative 2x. Okay, split this one up. What is your f of u?
Cube root of u.
A cube root of u, correct? And then the g of, I call it g of x, but it could be equal to u. That should be equal to
1 plus x.
1 plus x cubed, yeah. So if you can see how we're splitting it up, how we're grouping it together, then composite function, or finding the derivative of a composite function should be cake. The good cake, the fattening one.
Gooey
All right.
butter cake?
Huh?
Gooey butter cake?
I've heard of that. Never had it though.
It's good.
Yeah.
Sugar.
So using the general power rule, okay, and by the way, I meant to say you guys should go back and revisit differentiation, that when we did differentiation in chapter 2, remember that?
Yeah.
Back in the day, when you were young and stuff. Okay. And then compare it to what we're doing now, compare it to what's coming as we do the pipeline. So you know what to do when. So using the general power rule, so if u of x is a differentiable, which is why I just said what I said, differentiable function, n is any real number. This looks like hieroglyphics. When you read the definition, it doesn't even make sense until you do a question. So just take down notes for a minute, and you'll see the connection. And y, which is equal to our f of x, is equal to u of x to the nth. Basically how we differentiate, right? Then y prime, which is f prime x, in essence the first derivative, is equivalent to n times u of x raised to the n minus 1 times the derivative of u prime of x. Okay, that makes absolutely no sense when you look at that. I'm sorry. When I first saw this years ago, I looked at it and I said, oh, that's nice. What? All right. Then I saw a problem and it made sense. And then I connected the variables with the notation. Okay, so we start with a simple one, really. Find the first derivative if you have a function f of x which is equal to 3x plus 1 to the 4th power. Okay. So in essence, what's going to happen is, remember power rule? When you bring this forward, so this is going to become basically 4 parentheses 3x plus 1 to the 3rd. Does that make sense?
Yeah.
Okay, I want you to look at this. That's what that means right here. Okay? Times the first derivative of the junk in here. Okay, so in this case, if I take the derivative of 3x plus 1, I'm going to multiply it by just 3. That's what all this junk means. So now what you're going to do is we're going to multiply 3 times 4, so this times this, which gives us 12. And you're left with 3x plus 1 and all of this to the 3rd power. And that's how we treat composites, which is basically the essence of the chain rule. It's a composite function. Once you can identify it, you can work it out, no problem. So don't forget this is multiplied, which is why I'm multiplying 3 times the 4. Okay? So far so good? Not dying yet? Good. Let's look at B. Example B.
So 12 times 3x plus 1 to the power of 3 is the answer.
Yeah, that's the first derivative.
Okay.
Given the composite. So, okay, so this is part B. In part B, I'm asking you for the first derivative if the original equation y is equal to x cubed plus 4 to the 7th power. So what do you think? Mm-hmm.
X cubed plus 4 to the 6
Mm-hmm.
times
7.
No, what's it?
X cubed.
What's
3.
that would become 3x squared. Am I done?
No.
21x
Be multiplied, right? So, go ahead. 21x squared, times?
X cubed plus 4 to the 6.
Yeah. Now doing the math, that's where vaya con Dios, because this is a lot of work. That's a factor of 6 with a cube plus 4. Like I said, yeah, it takes a little while. But that I'm not asking you to do that. I just ask you to get the derivative. Yeah, done.
Just let you know that 21 looks like it's the one is part of the parentheses of the x squared. And
Here, we'll make it like that. Actually, let's get rid of these parentheses. All right. Is that clear? You're able to follow with me? Yeah? All right. So how many of you have been back to the STEM lab? STEM lab people? No? Getting tutoring help? No? Going back, reviewing that old test that will come back soon. Always. See you soon. And soon there'll be a second test, and then now you have got 2 tests. Don't try to establish a pattern where you're constantly reviewing them. I promise you it'll be worth your while. Okay, part C. We're looking for the derivative given 1 over t squared plus t plus 4 cubed. Think for 1 second what we did when we differentiated something like that. What did we do?
this wasn't this like the last chapter?
Yeah. What did we do?
Was it T over B?
I'm gonna raise it up and I'm gonna make that a negative. Because now I'm dealing with a simple equation. I'm gonna raise this so it looks like d over dt, parentheses t squared plus t. Notice that I am no longer a denominator, right? And all of this to the -3. Remember? Bring it below the line, up the line, it changes the sign.
Yeah, I think this times 1, you have to do the other rule because it's times 1, right?
Yeah. Even if it wasn't, you can still get away with it.
So it's T squared plus T plus 4.
To the -3 now.
To the -3. It just looks like 4 pluses, just, yep.
It's not 4 pluses.
It looks like.
It's not 4 pluses. How can I make this not look like a plus? Here, I'll highlight the plus and this plus. If it's not highlighted, it's a T, not a plus. All right, so how do we differentiate this guy?
-3
-3, parentheses,
t squared
t
plus
squared
t
plus
4
another t plus a 4,
so parentheses -4
to the -4, keyword,
then
times the derivative of this stuff,
2t plus 1.
2t plus 1. And can I re-express this again? So I don't have a negative exponent, because we don't like these guys.
You can just
Drop it,
Bring it down, yeah, drop it.
put it in the grave.
Drop it, drop it. -3, parentheses, 2t plus 1 over the t squared plus the t plus the 4. And now we're at a +4. And again, good luck. If you have to write that down all the way down, oh yeah. I mean, you can always differentiate again. That's an option. Okay, the last example. If you're having trouble following me, please stop me. Don't sit with your question. And I'm looking down most of the time, so make sure you get my attention. So find the derivative if h of w is equal to the square root of 3 minus w. What could you do to that to look kind of like the prior
You
one?
can just, instead of the square root, put the parentheses 3 minus w all to the 1 half.
To the 1/2, yeah. So if I do that, then I get 3 minus w to the 1/2 power. And now I differentiate. What do I do?
1/2
1/2,
times
3 minus w. And I still got a 1/2 here, but I'm going to subtract 1, which is technically now 2 over 2. So this actually is -1/2.
times -1.
And then now times the derivative of that, which is -1, correct. So what can I do now? Because I've got a -1/2 here. How can I fix that? So I can do 1 over 2, parentheses 3 minus w, raised to the 1/2 power. And remember, -1 kind of goes with that.
Can we keep it with the negative? Or how do we know when not to?
Well, because it's -1 times the 1/2, so it should be -1 over 2.
No, but I'm saying, can we keep it as a negative half? Half.
They're gonna mark you wrong.
Okay.
1 to 3, you got this?
Yeah.
You want to try 4 more?
Sure.
What?
Can you do this like forever? Just 3 minus w instead of.
Why not? You can do this, so you would do -1 over 2 square root 3 minus w. That would work. So again, it depends on the question. Okay, here, let me give you these to try. Because if you're doing this and you're able to do this, then I'm going to call this E, F, G, and H. So example E, I'm going to give you, find the first derivative if h of x is equal to 5x plus 2 to the third power. That's the first one. And I'm going to write the other one right below it. Okay, let's look at the first one together. What am I doing here?
Three times 5x plus 2 squared times 5.
Times 5. And this results in
15
15.
times 5x plus 2.
5x plus 2 squared. Yeah. And that's your first derivative. Remember, it's displacement, velocity, acceleration. So it's kind of like displacement. Sorry, my screen is cracked. Displacement is that first derivative. No, actually displacement is your original equation. My bad. That's your original equation. Velocity is your first derivative, your rate of change. Acceleration, that's your second derivative. So just derive from where you are. Okay, so dVA, displacement, velocity, acceleration. Okay.
So I get 5 because 5
Derivative of this. This is the derivative of that part of the equation. If I take 5x plus 2 and I differentiate it, I get 5. Okay, the second one is not any different from this. So tell me, what do you think my first step is going to be?
Put the 5 on the screen.
Bring the 5 in front. X to the fourth minus 5 to the
4.
fourth power times what?
4x cubed.
4x cubed. That's it. It's basically take the derivative. There you are. Differentiate. Final answer is 20.
X cubed times x to the fourth minus 5 parentheses to the fourth.
Yeah. Okay, let me rewrite that because that looks crazy. So yeah. So this is times x to the fourth minus 5 and all of that raised to the fourth power. That's not so bad. Okay. Walk me through G. How's that going to look like?
First you bring it on top as a negative, so you get t squared plus 4 to the negative 2.
Yeah, I got that.
Now what?
You get negative 2 parentheses t squared plus 4 to the negative 3.
Correct. Times
2t.
2t.
So we get
Can we-
minus 4t times t squared plus 4 to the negative third. Then you can bring the thing to the bottom.
I was gonna say, so multiply this gives you the negative 4t, and this has a negative exponent, so bring it down. Make it positive, so you get t squared plus 4 to the positive third power. Is it connecting for everyone?
Yeah.
Alright, I want to hear crying at the end of the period and slaying my heart. It's crazy. I went home and did a video right away. Did you guys watch the video? Are you using the videos? Because I'm not doing them for my health. Awesome. Alright, so what about this guy? What are we doing here?
You have 4 minus w to the power of 1/2,
Okay, so
and then you have 1/2 times 4 minus w to the power of negative 1/2.
right, because it's 1/2 minus 1, which is really 2 over 2, which results in negative 1/2. Okay, wonderful. Now what? There's something missing.
Times
Negative 1.
yes,
The negative 1 comes from differentiating
the w.
the negative w. Right. So what's my final answer?
Negative 1/2. No, negative 1 over 2 times 4 minus w to the power of 1/2.
Or,
Negative 1 over 2 square root of 4 minus w.
got it. Are you okay with this? I hope you are. Okay, wonderful. So let's look at example 4. And this is the example, the way they show this. I may have to color code so you follow along, but I think you'll be all right. Okay, so they are introducing, you've heard of U substitution. We've talked about it in here, no? U substitution? No? I didn't talk about U substitution? Okay, so here's a notation they're using for example 4. Example 4 deals with the concept of theorem 2 of the chain rule, which basically states that if some function m of x is equal to e times I to the x. Once again, it looks like hieroglyphics until you make a connection. And you know that this is a composite function. This is a composite function. Then you know that m prime of x is equal to the derivative of e times the function I of x, which is multiplied by the derivative of I of x, provided that they exist. Furthermore, they use a different notation. So I'll make the connection for you. So here, in case you missed it. So here's dy over dx. The derivative is equal to dy over du times du over dx. Okay. I mean, I can literally curse right now because I'm like, all right, because when you look at it, it doesn't make sense. But look, this is what they're getting at. This is example 4a. So I'm going to start with this one. If you pay attention, I'll bring it back to this. So in 4a, they're giving us that function m of x is equal to 3x squared plus 1 raised to the 3 over 2. So we'll do one at a time. There's 3 examples. We'll do one each. So you're gonna start with, if I do e prime of u, we're gonna say that this is equal to 3 over 2, and we're gonna call this u, and we're gonna raise this, because remember it's minus 1, right? So minus 3 over 3. So this will become positive 1/2. I prime of x, as they explain it, is equal to, in this case, the derivative of this. It's the same thing we just did, it's just a different notation, hence 6x. So putting it all together, what they're saying is that the first derivative of this m of x equation is equal to 3 over 2, parentheses, 3x squared plus 1, that's your u, raised to the 1/2 times that 6x. Does it look really different from what we've done? And yet that's the notation they're using.
The way you explain it, it sounds very, it makes it look the same. But...
And well, we're not even done though. Remember, we're gonna multiply these two, right?
Oh.
Because that's 18x over 2, which is really what? It's just 9x, right?
Yeah.
So the first derivative of this equation is equal to 9x times the 3x squared plus 1 to the 1/2. It's not that bad. It's just a notation. You kind of have to like get used to it, that's all. Okay. Oh, and don't forget that the u part of this equation, u itself, is the 3x squared plus 1. We're just leaving it out for a moment. Color coding it, it looks like this. This is your u. This is u. I don't know if that helps you. All right, and then all this that you see here, this I of x, is nothing more than the derivative of this. Okay, let me give you one question to try.
Where did the 1/2 come from?
Minus 1. Remember, it's always minus 1, which is really 2 over 2. Hence, 3 minus 2 is 1 over 2.
Okay, that's passing right back.
You with? Yeah. Okay, so do me a favor. Show me that you got this, and let's try this equation. If you raise your hand, you're lost, because you are in between the computer and make sure you yell at me if you need me. So I'm going to give you m of x is 2x cubed plus 4 to the negative 5. And so I'm just simply asking you to find the first derivative.
It's a negative 5.
Yep. Okay, so if you would agree with me, we're going to do, if you want to use a notation, we could do negative 5 u raised to the negative 6, if you want to do it that way. And this is going to be times the derivative of u, which is basically 6x squared. Very good. And so now we reduce it. What do you get? Negative 30x squared times the u part, which is, remember, u is a 2x cubed plus 4.
You would get 6x squared.
No,
I'm sure.
You already did the derivative, 6x squared.
Okay.
We're now distributing. So this will be the 2x cubed plus 4, and this raised to the negative 6.
Okay.
That's it.
Now you wouldn't drop down the it would be incorrect if you were to drop down the
Oh, you can drop it down, sure. Yeah, we can make this negative 30x squared over positive 2x cubed plus 4, all of this raised to the 6th power. Absolutely. Okay, if you felt okay with that one, let's try another example.
You have to do the U part, or can you just bring it down?
I tend to skip you, but
Why? Why do you skip me?
no, I don't. That's funny. I tend to do that, which is a bad habit, and I'm gonna tell you why it's gonna kick you in the butt. When we don't cover chapter 3.5, but if we do implicit differentiation,
It helps for longer equations when you have a really like big.
more convoluted,
Yeah.
you definitely don't want to skip
You don't
you.
wanna like spend your whole
It's
a long time just writing one term.
I was actually doing a course. I'm actually doing a course in algebra and geometry, kind of like a mix of abstract algebra. And they gave us an equation, very long equation for a polynomial. Talk about needing to substitute. Oh yeah. Okay, let's try this one. So we're still on example 4, so don't think I'm running away. This is example 4b, and they're giving us the function m of x is equal to e raised to the 2x cubed plus 5. Okay, remember the derivative of e to the x is basically, and the derivative of natural log x is 1 over x. So we're gonna hit those next. All right, so we're gonna start with b. So we start with the derivative, first derivative of u is equal to e to the u. We know in this case that the first derivative of I to the x is going to be the derivative of this part, which is basically 6x squared. So based on the chain rule, if I do m prime of x, that is going to equal e raised to the 2x plus 5 times 6x squared, which would simply result in 6x squared times e to the 2x to the third plus 5. The u part of the equation is right here. Okay?
Just so you know, you in the beginning of mx prime, you forgot to add the cube. You need to
Yeah, no, there's a cube there that did not go away. Do you want to try one? Let's try one before we go forward. So this is your try, and I'll leave that there for you to take a look at. So that's your original question. We're going to do m of x is equal to 3. I'm sorry, e raised to the 3 x to the 4th plus 6. So what's my e prime u? E to the u. What's my I prime of x?
12x cubed.
12x cubed. Okay, and then what's my m prime of x? What is that going to be? I'm listening.
e to the x.
E raised to the 3x to the 4th plus 6. We're done.
How did you get 12x cubed?
The derivative of this. The derivative of this gives you that piece right there. Just like in the prior one, you notice we have 6x squared. That comes from right here. Okay, now again, the derivative of natural log x is
1 over x.
1 over x. Okay, so on this one, this is example. No, it's actually, we're still in example 4, but part C.
Oh, fantastic.
So in this one, the function that I'm going to give you, m of x, is equal to natural log of x squared minus 4x plus 2. So as I'm setting it up, my derivative of e to u, which u is obviously all that stuff, is going to be 1 over u. So I'm just going to put this here to remind you. My I prime u, or I prime x in this case, is going to equal the 2x minus 4. In other words, the derivative of this. That's where this is coming from. So it's that derived. And so based on the chain rule, my m prime x is going to be equal to 1 over x squared minus 4x plus 2 times 2x minus 4, which results in 2x minus 4 all over x squared minus 4x plus 2. Not bad, right? It's easier to comprehend. Okay, and so your try question for this one is the m of x is equal to the natural log of x squared plus 9x plus 4. You start to notice a pattern, don't you?
Yes.
For the natural log one. So, I mean, remember they're doing the long steps to help you understand this, but sometimes too many steps is too much. If I know that this is simply 1 over whatever this entire value is, which in this case is x squared plus 9x plus 4, all I have to remember is that I'm going to use 2x plus 9 over 1 times that. This is basically the derivative of this. Do you notice the pattern is simply this will be your numerator over the denominator, and that's it. It's that easy. Okay, so if you're taking good notes, that's good. Okay, example 5. In example 5, they're giving us for the following, where I have y is equal to h of x, and that is equal to e raised to the 1 plus natural log x, all of this part squared. They want to find the first derivative. So find dy over dx.
It's e to the power of 1 plus ln x squared.
Yeah.
Right.
So immediately I'm looking at this question, I'm thinking, well, this is the equivalent of y equal to e to the w, or any variable you want to use, where w equals 1 plus u squared, where u is actually the natural log of x. It's a lot of steps here. So here's a natural log of x. That is my u. If I look at this function, that's why this is u squared. If I look at all of this part of the function, just this part, this is my w. Just make that connection for a minute. And now this is where they started that crazy notation. So I just want you to see the connection. So the first derivative dy over dx is equal to dy over dw times dw over du times du over dx. Okay. Patiently follow me. It'll start to stick like glue. So this means that I have EW. This is times 2u times 1 over x, hence the derivative of natural log x. So EW comes from here. This is EW. This is where the 2u comes from. And this is where I have 1 over x, hence the natural log of x. Okay, my next step, and I did state, did I put that down somewhere? Where e, this is e raised to the 1 plus u squared, again, times 2u, times 1 over x. This is a u, not a w. Which simplifies as I continue as e to the 1 plus the natural log of x squared times 2 natural log of x times 1 over x. And your final answer here, if I do the math, basically will be 2 over x times the natural log of x times e to the 1 plus the natural log of x squared. If you're having trouble following the math, here's your 2 that comes from this. Here's your 1x, I guess. I'll circle it, put it down here. The natural log of x is this piece, which is left over. And the rest is history, that's that part, which is right here. So this is how they apply chain rule to this question. So I'll show you that for a minute, and then we'll try one together. Let's take a moment. Can you read that back there? Are big enough? Yeah. You know, it's interesting. When I first learned it, I thought, well, what a load of crap. Why do we have to do all this, right? That's a lot of work for what? And then I saw the applications, which are when you talk about dynamic systems and functions of dynamic systems, where you have one thing and, you know, kind of like it works together with something else, kind of like your air conditioning system, where you have all those pieces running together. This math comes in very handy. So. And if you don't make the connection today or next week, it'll eventually click for you if you have enough time in the day to think about this for a minute. So Fluid dynamics, anybody? Physics? Fluid dynamics? Composite? No, nada. How many engineering majors? Anybody in here?
Used to be.
What happened? Not your passion? No. I always say engineers are really good future math teachers. That's always been my that's
Yeah, I
always
like
been my
math,
take.
Just not all.
Yeah. All right, let's try an example. I'll leave this up here and see if you can guide yourself with the steps. So here's our function. We're going to find that first derivative given h of x is equal to natural log of 1 plus e to the x to the third power. All right, give it a shot. Take a moment. See if you can walk yourself through these steps. So how would you label these at all? Where would you start on this set here?
Y equals 1 over W.
So y equals 1 over w, okay?
And W equals 1 plus e to the x.
Okay. And you?
I cut it differently. So for my, what I put for y is y,
Use just
y equals wq. That's what I put it.
Okay.
No, just y equals wq. No.
Oh, you're ignoring the fraction. Okay.
Oh, wait, there's a frac.
All right, I'm gonna give you a minute. Think about it. Remember, what is the derivative of natural log x?
1 over
1 over x. Remember that. What's the derivative of e to the x? Here, let me help you one more time. What if I said to you that first derivative based on this should be 3e to the x natural log of 1 plus e to the x, but this time squared.
All over 1 over
All over
1 plus e to the x.
1 plus e to the x. There you go. Where'd I get all that? Make the connection. What happens if I think of this as 3, or let's say hypothetically we talk about this as w to the third. So if I have w to the third, and I do the derivative of that, isn't this 3w to the second? So start thinking about, well, here's where the 3 comes from, here's where that comes from. So now what's our w? What's the actual value of the w?
Ln of u.
Wouldn't it be simply 1 over? Call it u if you want, yeah.
Yeah.
Right, because then that means that this is 1 over that. Okay, what else do we know? What is u?
E plus e, 1 plus e to the x.
1 plus e to the x.
So you got those.
So 1 over u, this is where the 1 over 1 plus e to the x comes in. And this is just the original equation, just like we did here. We left it original. 1 plus natural log x. And again, what's the derivative of e to the x?
E to the x.
It's e to the x. That's why we have that here again. All right, we'll revisit some of these. I want to see if maybe I can do this with you again. On one of the practice days, we could throw some questions around. It would be fun, but would be good practice. Let's do the last examples. And so this is a hodgepodge of questions. So this is example 6. And so we're using general derivative rules. General derivative rules. We're almost done. Hang in there. I see a couple of you fading on me. So general derivative rules, they're giving us 3 little examples. So we're going to start with A. They're asking us for d over dx given e to the 2x. They're asking us in part B, we have d over dx natural log of x squared plus 9. And for C, they're giving us find d over dx given 1 plus e to the x squared to the 3rd power. Alright, so this is basic derivative rules and differentiation. So let's take 5 minutes to try it on your own, and then we'll do it together.
Can you scroll up so I can see
Where are you?
on the last?
Oh, I have to take this off the screen. It's another page. I'll bring it back. Okay. No, still some time. Okay, if you look up, I have the first one. What questions do you have for me on this? Do you understand the notation here where I say find the derivative of that exponent? What's the derivative of that exponent? Just 2. And then basically, if I know that the derivative of e to the x is e to the x, this is just going to be 2e to the 2x. Right? All right. Part B. Let's look at part B. In part B, I gave you the derivative of natural log, so d over dx of natural log of x squared plus 9. Okay. So step 1 is the natural log of x is, if I said to you natural log of x,
1 over.
yeah, 1 over, and in this case x squared plus 9, right? Because that's the first derivative of that. Right? Okay, and now we're going to take d over dx of x squared plus 9. Well, what is that? Yeah, this is just 2x. So I have really final answer of 2x over x squared plus 9. That's my first derivative. Does it make sense? Yeah, no? Okay. The third example I threw at you was this one. I hope this one will also help you with the prior one. So in this one, if I do the d over dx of the original equation, I'm going to get 3 parentheses 1 plus e to the x to the second power. Does that make sense?
Yeah.
Okay. D times d over dx of the original 1 minus e to the x squared. Which means that I'm looking at 3 times 1 plus e to the x squared, e to the x squared, which is this little piece here, d over dx of that exponent x squared, which is basically 2x. So I have 3 parentheses 1 plus e to the x squared times e to the x squared times 2x. All right, and then this simplifies further. If I multiply this times this times this, then I'm going to have 6x e to the x squared, and all of this times 1 plus e to the x squared squared. All right. I'm going to throw 3 questions at you. You don't have to do them now because you're going to be over the class time, but try them while you're, doing your homework and such. So try, and I'll start the class going over this. So we have d over dx of natural log of x cubed plus 2x, and part B, I want you to find the derivative if I give you d over dx e to the third power x squared plus 2. And the last example I would like for you to try is this one, which is d over dx times 2 plus e to the negative x squared to the 4th power. All right, give those a shot over the few days, or a day or two, and then we'll start the class talking about these.